All right. Welcome to the Thursday afternoon plenary session. My name is Brad Swatsky. I'm with Jefferson Lab, for those of you who haven't seen me before. Just a couple of sort of public service announcement slides. First of all is the closing event, which I hope you all are aware of, happening at the Blue Moon Tavern, or Tap House. That should be Blue Moon Tap House tonight at Waterside. A couple of important things. It's since it's an open restaurant, do bring and wear your badge. It's going to be a full house, so we certainly don't want to turn anybody away, but yeah, do bring and wear your badge. Doors open at 7 p.m. We ask that you all come in and enter on the ground floor. There's two entrances. There's the harbor entrance as well as the street side entrance. Doesn't matter which one, just come in around 7 o'clock. Let's see, we've got so food and open bar for beer and wine from 7 to 9. You don't have to worry about drink tickets, so you can all enjoy yourselves. There'll be a buffet and food and all sorts of good stuff. Jay Sennett, fantastic band, will be playing outside in the open air. What do we call it? The auditorium, the concert band house. There is a skyway path from the hotel that I mentioned yesterday, or that we mentioned yesterday. So you can use that if you want to get over there without crossing streets. We will be doing a group photo. So the plan is here. Attendees are going to assemble on the outside, on the harbor side of this venue. If you've been to the water side, you'll know what it looks like. You'll just sit in front of the stage where the band is, or stand rather in front of the stage where the band is. Photographer's going to be up on the Blue Moon second floor balcony taking a shot down. So please head out around 7:20, and we are going to take a photo at 7:30 sharp for everybody who is there. We'll have people yelling, so listen for that and follow the instructions to kind of guide you out into that general area. And one more extremely important thing, since I know some of you folks have to catch flights in the morning and may not be around, we wanted to make very sure to thank in particular, the track conveners and the program committee who did an insane amount of work. This is the first conference on this scale that I've been involved in, and I was amazed with the logistics and just the sheer amount of work it takes to put something like this together. I think it's gone really well, and I just wanted to highlight and thank those folks in particular for such a fantastic job. Of course, these are the same folks doing moderator support for the breakout sessions, and their job is not yet over, so they'll be doing proceedings and supporting the proceedings, the written proceedings that will follow the conference. We will let you know and give you some more information on that for those who wish to participate. Fantastic. So thank you all very much. I will now hand off to our moderator for this afternoon, Tori, and we'll get on with the show. Thank you.
Okay. Hello, everybody, and welcome to the final plenary before the summary plenaries. We've made it this far. This one on upcoming computing challenges beyond high energy and nuclear physics. I'm Tori Wenas from Brookhaven National Lab. I head up the nuclear and particle physics software group there. So we're gonna, let me just say about questions during the question period. You can either raise your hand for a mic to come to you, or you can come to the two mics in the corridors if you like. I think that's all the upfront business I have to do. So let's get right into Maria Elena Monzani is going to tell us about here. I had it all queued up so that I wouldn't miss it. Data intensive searches for dark matter with LUX-ZEPLIN. All yours.
All right, thanks everybody. Let me put a watch on here. It's a pleasure to be here. I thought I was doing high energy physics, but clearly not. This is me finding out for the first time. But anyways, I'll talk a little bit about dark matter, which I believe you heard about on the first day of this conference. So dark matter is all over the place. We can see the effects of dark matter on a variety of cosmic scale, starting from single galaxies, clusters of galaxies, the whole universe. And if we weigh the composition of the universe, we get something like this pie chart. Most of the matter in the universe does not interact with light, doesn't emit or absorb light. And as the mainstream media reported it, most of the universe is missing. This was taken outside the newspaper stand in the UK in 2000, 2005 when the WMAP data came out. This is a very humbling perspective about our work. There are 3 ways to look for dark matter, and I would like to thank the amazing graphics department at SLAC for these cartoons. We can try to make dark matter at the collider. You've heard about colliders all week this week, so I'm not gonna say more about that. You can look for annihilation of dark matter particles in compact objects in space. This kind of observation can be done from a ground-based experiment or from a space-based experiment, such as the Fermi Gamma Ray Space Telescope. Or you can do a scattering experiment, which we're all familiar with. And those experiments are usually done with a bucket of nuclei or a tower of nuclei under a mountain. The experiment I work on, LUX-ZEPLIN, is located at the 4850 level of the Sanford Underground Research Lab, which is in South Dakota. It's exactly a mile underground. The name is an acronym of acronyms. I apologize, I did not choose the name. This is the famous day discovered where the first observation of solar neutrinos happened in the late 60s. So I'm gonna say a little bit, oh, by the way, this photo shows a little bit, gives you an idea what a bucket of nuclei looks like. So I'm gonna give you an idea of data rates because my talk is titled Data Intensive, so I wanna say what we mean by that. This is the Fermi Gamma Ray Space Telescope. The 15th anniversary of launch is coming up in exactly a month. I wanted to talk about Fermi because Jana and I used to work on it a long time ago. It's our baby still, although it's 15, which is in telescope years, probably 85. It's taken a little over 80,000 orbits, 800 billion triggers, and 2 billion of photons are available in our public data set. This gives you an idea of the data rates. This is our trending plots. At the detector, we have anything between 1 and 5 kilohertz, depending where the spacecraft is in its orbit. We download about 1/8 of those events. We do an aggressive event reduction on board because waveband is, how do you call it? Data band is very expensive in space. Then we do a couple of levels of reductions in analysis, and we go down all the way to 1 hertz. So it's about at least a factor of 1,000 reduction. The thing highlighted there is the brightest event that we've seen so far, and we need to go down by a factor of 1,000 in cleanup to just see it on a trending plot. So Fermi so far has written about 5 petabytes of data to disk, and about 0.1% of those data is clean gamma rays. This is something that I find very meaningful. All Fermi data and software are open. This is a successful open science experience, which made my job as the owner of the Fermi data set very rewarding because it's a data set that I don't actually own. It's hosted at the High Energy Archive at NASA, and we release all the data, all the analysis software, the instrument response function, and the background model, specifically background and foreground. So this can be done. There is phenomenal community engagement with our data. 90% of the papers published on Fermi data are produced by non-collaboration, by outside collaborators, by outside scientists, and those scientists also do a phenomenal quality control of our results. So if we claim that we found something, if it's false, you're gonna hear about it in a couple of weeks, and we have so far. So I'm gonna move on at underground physics. I wanna show you how we build a direct dark matter detection experiment. In our case, it's just a bucket of liquid xenon. So first of all, take a lot of photos so you can go show it off to your friends. It's about 10 tons of liquid xenon. Fortunately, liquid xenon is very dense. It's a density of 3, so aluminum floats on it. So 10 tons of liquid xenon is about 5 feet by 5 feet. Amazingly enough, we're trying to detect dark matter with light. The liquid xenon recoil, it's transparent, it will produce photons. So we have photosensors array, 2 arrays of 500 photosensor each. All our data is at threshold. Most of the sensitivity of the experiment is at threshold, so we take a lot of 0. We have a lot of 0 in our data set. This is a scale of the channel number. The bucket itself is ultra high reflectivity Teflon, which we assemble like a Lego. And then, this is the mating of the bucket itself, the Teflon bucket, to one of the PNT arrays with the crane. And then this is the finished product. So once you have this, empty bucket, you put it in a double cryostat, you wrap it up, bring it underground. This was October of 2021. You can see in South Dakota it snows pretty early. The tower there in the drawing is the head frame where the miles of cables are spun up. And here is the arrival of the inner cryostat with its protective shielding at the 4850 level of surf. Just to give an idea, this elevator ride took about 2 hours. When we bring humans, it's about 11 minutes. So we're a lot more careful with instrumentation than we humans, or humans are more resilient. So here's the thing, everything's radioactive. So there's been maybe, like, depending how you count, 30 to 40 years of R&D for the materials that went into this detector. And the stuff that it's built off is about between 100,000 and 1 million times cleaner than regular anything. So we have titanium that is 1 million times cleaner than steel, the commercial steel, the plastic, all the handling, etc. Even with that, our trigger rate is about 50 hertz. This is basically all background, billion counts per year, or 5 petabytes in 3 years, approximately. So it's the same as Fermi, but in a 1/5 of the time. This is, LHC, old style LHC level of data rate. So we're talking about massive, massive, massive is a big word, significant data volumes. How much of this is dark matter? So there are about 3 dark matter particles per liter on Earth. So my coffee cup has maybe 1, I don't know, ounces to liter. We're slamming against the halo, the dark matter halo of the galaxy at 230 kilometers per second. So in my bucket, we have about 1 billion particles that go through every second. If we're lucky, that is, if nature cooperates, we're hoping to see maybe a handful per year. We designed it around 20, 25 dark matter particles in a 3 years run. That is to compare to 1 billion per year of background. So it's an extreme needle in a haystack problem. So that's how we feel about our data set. I'm going to skip over algorithms for now, unless you have specific questions. And I'm going to show you some of the tools. This is one of our supercomputers at NERSC, the per-murder supercomputer. I was very, very happy the first time I was allowed into NERSC to take a picture with it. We take data 24/7 and we automatically process it at NERSC, copy it over at NERSC and process it. We have large-scale simulations with detailed modeling. So we build the experimenting software before we built it for real, which is nothing new for the LHC people. And we had an extensive campaign on mock data challenge, which again is nothing new for the LHC people, but for the dark matter community, this was the first time we did it. It was a very hard sell. So what happened here is we did a 3 months science run last year. So it was a Christmas to Easter. We didn't do it on purpose. And then we published 5 weeks after the end of the run. So it was a very quick turnaround because I made them rehearse the whole thing 3 times over the 5 years previously. Again, didn't make that many friends, but the students told me the data challenges were a lot harder than the actual science when we had the real data. So this is what ideally our data will look like. The orange shows this is calibration data. The orange is a neutron calibration source. This is where the dark matter particles will show up. And the blue is a tritium source, which is a very good approximation of where all our background will show up. So this is the ideal case. Orange is dark matter and blue is background. This is what actually looks like once you turn it on. This is our 3 months data. It's 100 million events, a number like that, 10 to the 8. So we do several rounds of cleanup using the topology of events in the detector. Again, I'm not going to do the details right now. Here are some of our main event selections with their efficiencies. A big one is Like I said, xenon is very dense, which means all nuclear reaction and all gammas stop at the edge. It's basically like a wall that stops all radioactivity. So 90-something% or 85% of our events happen at the edge of the detector. This plot is reconstructed radius versus depth. So most of the stuff shows up on the edge. Remove the edge and use the inner 80% volume of the detector, which is bound to be very quiet. Oversimplifying here. But the data set cleans up real nice. We have 300 events in total. Once you do all your data quality cuts, and then we have a very, very detailed background model, which again, I'm not gonna go into, but you know, the purple, or where it says 30 GeV WIMP, is where we were expecting to see dark matter. Data are best fit with 0 dark matter interactions at every mass, which is, we didn't find dark matter, spoiler alert. By the way, you would have heard before I showed up if we had found dark matter last year. So it's not really news here. So we don't find anything, we put a limit. We say this, finding nothing better than everyone else. So we go down in sensitivity, explain some model, rule out some models of dark matter particle. What I showed you now was 3 months of data. We have 3 to 5 years of data coming or in the can. And so there is more sensitivity coming. So lots more data. There is real discovery space left, but what is exciting to me is not the discovery space, not only the discovery space, sorry, not trying to get fired today. It's the amount of data that we're gonna get. And like I said, we're talking about 5 petabyte. What my group is working on is reject and physical detector effects, because every time we do one of these searches, we find a lot of unmodeled or unexpected backgrounds. And we've been looking at anomaly detection. There were 2 talks earlier this week about from graduate students at Stanford working on anomaly detection. Here is one example. This is from the Google Cloud blog, what anomaly detection looks like. And here is what it looks like for LZ. This was in the dissertation of Maris Artus, who's a postdoc in the Slack group now. So you will see here that there are stuff that are very far from everything else. Those are very obviously detector anomalies. So I'm going to spend the last 10 minutes of this talking a bit about our computing architecture. We have a redundant architecture, which we could argue is a bit much, but we have 2 full copies of the data. So data is staged at the Stanford lab, where we have very minimal computing infrastructure, and then it's relayed to the US data center in NERSC. This is where we do the prompt processing, the long-term archiving on tape, and where we have supercomputers, like I said earlier. Then we have an additional data center in the UK, and that's where we mostly do the reprocessing and the simulation production, and the architecture is very different. It's grid, it's distributed, it's regular Linux CPUs. So we have a fully redundant design, 2 complete copies of the data on disk, plus a copy on tape, and either data center can perform either simulation or data processing, especially reprocessing. Pros and cons. We have an exceptional level of risk mitigation. Cons, we have the architectures are very different, and because one is in Europe and one is in the US, the policies are very different. So authenticating data back and forth, takes one of my best engineers almost full time. We got them extremely good at software portability. I learned things I didn't know it was possible to know. Our students and postdoctoral scientists can comfortably program on a supercomputer or on the grid, which means we have a really hard time holding on to them because they're very good at computing. So what do we do in NERSC? We do the real-time side of this operation. We process our detector data early and often. Like I said, we do automatic 24/7 reconstruction when the data comes in. And we have the possibility to reprocess multiple times based on calibration. So we can turn around a year of data in 1 month. Time is of the essence. Stefan Lewis presented on our on-site computing infrastructure earlier this week. We have very minimal computing infrastructure served. We have a very beefy RAID array, redundant, and we can do a first look quality monitoring. We don't do full reconstruction. So the data quality monitoring and the assessment of the detector health happen in NERSC. So we do a quasi real-time analysis feedback, and especially during commissioning when we were setting up the detector. I'll come back to this. And one thing that they asked me to talk about at this conference was, what do we do with SPIN? SPIN is the container as service platform at NERSC. It's where we have all our web tools, our databases, our production and monitoring tools, and part of the user and data access is done at SPIN. Again, container as a service platform. This is taken from the NERSC website. So this is free advertisement for them, deployment of science gateways, workflow managers, and web services. And it seamlessly integrates with NERSC compute and storage. So we build our containers on Docker, they're shipped out, and they run on Rancher. I'm going to show you a couple of things that we do with SPIN. We monitor our data movement. Here are a couple of plots that show, the data volume coming in from surf automatically. The latency, this was a very slow latency because we were calibrating. Usually the data comes in within 10 minutes. And then this is the data processing, how long it takes to process a run. Queue management, we do that with RabbitMQ. Anyways, nothing very spectacular. You've all seen something similar in your day job, but this is done on SPIN. One thing that people in LZ like very much is the offline event viewer. As I said, our sensitivity is all at threshold, so we need to be able to inspect the single waveform by eye, and then we look at event maps. So this specific event is a double scatter. You see two peaks very close to each other, and it's from the edge of the detector up, left corner. Yeah, and 9 a.m. This is very popular. Every few months in LZ, we do what we call a hand scanning challenge. And here are some of the plots of some of the charts of concurrent sessions during the hand scanning challenge. And we can have about 50 concurrent connections, or about 300 in a day. We made t-shirts of those challenges. This is a very popular tool. I highlight this tool because this was entirely designed and built and maintained by Thayer Anderson, a graduate student in our group. This should give you an idea of how straightforward, he's a very special student, but still, he's a grad student who could set this up quite easily. It's not even the main focus of his dissertation. So to talk about our experience with SPIN, ease of use and the level of training are definite pros. I'm not a grad student. I'm an old lady and I'm mostly a manager, but I was able to build a web page with full authentication in maybe one afternoon after going to the training. My web page is a collection of links. I didn't do anything fancy, but this gives you roughly the idea of how low the barrier of access to SPIN is. The big pro is the integration with NERSC CPU and GPU and storage. The big cons, the integration with NERSC compute and storage, because there are multiple NERSC resources that pull into this thing. If one is degraded or unavailable, everything goes down. Scalability has become a challenge. SPIN has been very successful, a bit much, I would say. And so we're having a little bit of scalability issues, isolating the dev instance. The underlying file system is not good for database, which is one of the applications we have with it. And so it's growing. And then speaking of database, the policy, this was designed as an experimental system. Now everybody's using it, and the policy is evolving with the tool, which is creating, requires, let's say, adaptation or flexibility on our end. So I would like to say, speaking of reliability, my top 3 priorities for any real-time computing system are reliability, resilience, robustness, and the 4th one is uptime. Downtime is very expensive because we have to engineer around it, and because it impacts our reputation with the science partners. And like I said, we use so many parts of NERSC that degradation in anywhere impacts the entire workflow. I'm going to give you an example, a successful example from commissioning. Here is the leveling campaign. TPC is, LZ is a liquid TPC, so we had to align the liquid, and it took 3 days. This went, that's the way we did it. Went down in the morning to data, processed it in the afternoon, and then somebody overseas looked at it overnight, went down the next day. We had 1 week to do it, and every week in the commissioning had different experts fly into to the lab to commission their piece. So we had a week to do it. Now, the underground week has surfaced 4 days. That week was Monday to Thursday. Wednesday was going to be a nurse outage. So we would have lost the week. And then if you start rescheduling all the people, it's easy to lose a couple months. They kept us running on a backup system. So that's something we're very grateful for. But this is to give you an idea of the importance of system availability, which is the number 1, 2, 3, 4, 5 concern for real-time computing. That's pretty much all we care about and all my collaborators care about. Because if you have 5 petabytes of data and can't access it, these people are going to be very, very unhappy at me. This is my team, the LZ collaboration. This is a subset of them. It's a pre-pandemic photo. We have about 200 nurse users. Most of them use the platform fluently. Here's a list of our funding institutions, about 35 funding agencies, about 35 institutions all over the world. And again, you probably heard of Dune this week. The tower in the back is the Roche shaft, which is the Dune cable, is spun up. And I think I can stop here with, oh, I had 2 minutes left. Now I have to take all the questions. Thank you.
Terrific. Thank you, Maria. Questions? While people think of them, how cleaned up is the data that you make public?
Sorry, I didn't hear you.
The data that you make public, how cleaned up?
For Fermi? Or for, the LZ does not have public data, unfortunately.
Okay.
The LZ only publishes the points of the limit plot, so not a lot. Sorry, we only publish that curve. For Fermi, it's clean at the Hertz level, so it's a factor 1,000 cleaner than what we get on board, but it's still like, so we have 3 levels of cleanliness, actually 4 now that we publish. And so if you're looking at the transient event, something that's very quick, you can deal with more background. Or if you look at the localized source, you can deal with more background than if you're looking at the whole sky in a static fashion, basically. So we have 4 different levels of cleanliness or purity, and for each one of them, again, we produce instrument response function, background model, software, et cetera, so people can pick and choose depending on the science analysis they want to do.
Okay, thanks. Where? There, here we go.
Sorry,
I'm not seeing. Okay.
Okay. Thanks for the very interesting talk. I remember you said the data rate for background runs are about 1 petabytes per year, but I'm wondering what is the peak data rate you ever have during your calibration process, and if that creates any difficulty for your computing infrastructure, because you also said there are limited facility on site.
Yeah, so our peak data rate, and forgive me, I don't remember the number off the top of my head, is during neutron calibration, which is the orange thing here. We shoot DD neutrons at the detector, and I'm gonna say 500 megabytes per second, which is not a lot, but that is twice as much as our bandwidth. Don't quote me on the 500 megabytes, my brain is resetting right now. So we designed it to be able to take data for 8 hours during the day, and if it's twice as slow, we copy it over during the night. Then after we designed it, the modality for running the source changed, and so it's more like we sped it up a little, and they run it for a week, and we are a couple of days behind at the end of it. So we try to alternate high intensity sources with lower rate sources.
So thanks a lot. The presentation was very entertaining. I was wondering, since you mentioned these two systems that you run on, how you make use of NERSC's GPUs. So your data processing algorithms, do they require GPUs? Did you implement algorithms with and without GPUs? What did you end up doing?
Excellent question. So the first one is in simulation. Our simulation, 99.something% of the CPU time is done doing ray tracing. If we do full simulation for Giant, it's mostly ray tracing. So actually there is a one of the people in the photo of LZ is now a NISA fellow at NERSC who's working on GPU acceleration for ray tracing, because that's exactly what it's designed for. And it will give us a very big speed up in simulation and accuracy of the simulation. So that's the first one, low-hanging fruit. We haven't used fancy machine learning algorithms in our first result. I think this thing with doing the anomaly detection, we want to do a training at scale on the 1 petabyte level data set, and we probably will do it on the GPU using,
I guess my hidden question was that since you mentioned that partly you're running on a regular grid site, whether you guys figured out how to use GPUs on regular grid sites, but I guess not yet.
So here's the thing, regular GM4 with energy deposit, we don't need GPU. And the reconstruction that we do is very simple, it doesn't need GPU. So we have specialized uses for the GPU, and we're not forcing the UK people to have GPUs, although our collaborators at Bristol have 200 GPUs, and they've been co-leading the photon ray tracing effort with the person at NERSC.
Okay. Thanks a lot.
I have another question. You said you did 3 data challenges, but it took a lot of convincing. Did the first one take a lot of convincing and then people saw the value, or was it difficult all the way?
I would like to be polite here because I'm being recorded. The first one took a lot of convincing and it succeeded, and that made my life way harder. It was not, there was a predecessor experiment to LZ, which was called LUX. The data chain was sufficiently different that I didn't believe it would be a worthwhile exercise to do a data challenge with the LUX data because of the way the data chain was designed. That did not go down well for the LUX crowd. They were very offended that I didn't like their experiment, and they still are. Sorry, I'm trying to be more polite. This is the nicest way I can see it. But after the first one succeeded, we made increasingly sophisticated models, and the hope was that the first one wouldn't succeed. So we will stop playing around with simulation and actually squeeze out extra physics from an experiment that had been commissioned in 2015, I'm gonna say. I don't remember. Yeah, it was decommissioned 2 years before we started the mock data challenges. It was a difference of opinion that still very much is present in the experiment.
Thank you. Any final question? There's.
Yeah, thank you for your talk. Can you tell us if you found any interesting clusters in your algorithm that maybe showed you details about your experiment that were either unexpected or surprising in any way?
Yeah, so I'm sorry, I don't have the details here, and I'm gonna try and see if I can use the pointer, but this pointer is challenging. Let's see. This event here was, I don't remember what they are, but see this blue stuff. Let me say this way, we use the regular clustering with UMAP and DBScan to find where our reconstruction algorithm, our pulse finding specifically was failing. So I showed you earlier the multiple scatter, the double peak. It took a lot of iteration for that model to find the beginning of the event correctly, and it still finds fails in a handful of events. So what we've done so far with the clustering was to tune the pulse finding algorithm. Every time we open one of these blind or salted data set or any anomaly, any bias mitigation, we discover the type of background which we didn't know existed and has the same rarity as the target sensitivity as the experiment. So the new thing of finding new backgrounds, we haven't done it yet. That's my personal ambition, or the ambition of my group. That's what we would like to try to do. So far, we've only done, we've only found algorithmic failures of the standard reconstruction algorithm. So we used it for tuning.
Thank you.
Let's thank Maria Elena again. Thank you very much. Okay, and next we'll have Jana Thayer from SLAC talking about massive scale data analytics at the LINX coherent light source. Can I, before you start, after this session, there are the student poster awards. So be sure to stick around for the student poster. Yeah, very brisk 5-minute thing.
Okay, so here I am. My name is Jana Thayer. Maria Elena told you about the dark side and dark matter, and I'm here to tell you about the light side. The X-ray, like the LINX coherent light source, which is a big X-ray laser. I'm the leader of the LCLS data systems division at SLAC, which means I'm responsible for the whole of the data system that reads out, manages the data, and provides an analysis framework for analyzing it for the entire facility. It is a user facility, and before I go on, I want to make sure I acknowledge all of the people who are actually doing the honest work while I wander the world and talk about it. So there's the list of people that should deserve all of the credit for all of the good things that I'm about to say. So as Maria Elena mentioned, before I actually talk about LCLS, I also worked on the Fermi Gamma Ray Space Telescope. So I was responsible for the flight software on that instrument. GLAST, it used to be called GLAST. They rename it after it goes on orbit. But Fermi Gamma Ray Space Telescope is great because it's like a little particle physics detector in space. And you see, I'm a lapsed particle physicist. It's been about 20 years since my last CHEP conference, so it's been a while. It's nice to return to the fold. GLAST was great because it was a particle physics detector in space, but it had to be built to a certain standard because you couldn't send a graduate student up to fiddle with a cable or replace something if it broke. You also had to work with a processor, which is not the best processor on this planet, but probably the best processor on other planets. And you had to squeeze a lot of software into that small package. So we had to squeeze this data compression and filtering software to take the data rate from 10,000 hertz down to a kilohertz before it could make it through the modem, essentially. And every hour and a half, it dribbles data down to the ground, probably making that horrible screeching sound when it hits white sands. So from there, I went over to the LINX coherent light source and started working on this X-ray user facility. And so I will tell you a little bit about what this facility does, what I mean by massive data quantities in this case. And I'd like to touch on some of the workflows that we employ and how we use edge resources and high performance compute resources together to try and develop a lot of real-time analysis workflows. So here is a picture of the LINX at SLAC, heading west into the sunset, into the hills. So actually this is looking, yeah, it's looking west. So the electrons come down the line, they get accelerated. This should look familiar, this linear accelerator. Electrons get accelerated, and then when they hit the undulator, they get wiggled back and forth. And when they wiggle back and forth really, really fast, they generate this coherent and bright pulse of X-rays. The electrons then get unceremoniously dumped, and the X-rays proceed down the line to the near and far experimental hull. So you can think of this more like a fixed target experiment. We're not sending a beam around and bashing things into each other. In this case, we're sending photons down and bashing them into whatever sample we put in their way. The photons scatter off that sample and then hit a detector that sits behind or surrounding that interaction region. And then we capture those images and the data from that, and we figure out what it is that we hit and what that structure was. And that is where it gets fun. And this is where, unfortunately, my video will not play. So it will remain a black box to all of you. The instruments are quite complicated, and the X-ray pulses from LCLS are used like a strobe of light. It takes pictures of atoms and molecules at the level of, at the atomic level. The processing of this data requires a lot of computational power, and mostly you need to know what's happening in real time. So we're getting these pulses down 120 times per second now, very shortly 1,000,000 times per second. So one megahertz trigger rate. The cameras and equipment that surround the interaction region differ with every experiment. So you might have a large planar detector, a 16 megapixel detector that's reading out at 10 kilohertz one day, and another day you have one that reads out every minute. Sometimes you have one that reads every minute and a bunch of digitizers that read at a megahertz. And any given week, you have a different combination of things. So imagine if your particle physics detector changed every week, and you had to be able to adapt your DAC, your trigger, and your data reduction to suit. That is my challenge. So it's very difficult to do. So like I say, this is a user facility, which means that we have people who are awarded beam time, and they come from a lot of different fields: biology, chemistry, material science, matter in extreme conditions, and they do a variety of experiments. They have about 5 days of 12-hour shifts to take their data, and they get it and they have to process it, and they want to turn it around in real time. And so this gives you a snapshot of about 6 of the different workflows that we have. We have something like several hundred experiments per year, and thousands of users that come through every year, and everyone is at a different level of sophistication when it comes to computing and analysis. They are all experts in their particular field, and they are interested in their science. And so what I've shown here is the numbers for what the amount of computing it takes this year and in a few years when LCLS-II AT turns on to reduce the data and to analyze the data. And you can see that it's all over the map. Some things take a teraflop and other things take closer to an exaflop to do. So a word about how this life cycle goes. So what does it look like to be a user at LCLS? Usually you come in, you're awarded beam time, you arrive with all your equipment, you set up, you have 5 days, 12-hour shifts. During data collection, when you're taking data, you might be putting new samples in the beam all the time. And so when I look at the signal on the detector, I don't know if my detector is going to have high occupancy today, whether signal to noise is a problem, or whether I'm going to have a low occupancy signal, or whether I'm looking for some diffuse scattering between bright spots. So I don't know what I'm looking for on any given week. I don't know what the science is. I have to be able to handle it all. The experiments themselves require a lot of fiddling to make sure that the beam gets aligned, that the optics send the beam onto the target, and that they get the geometry of the experiment right, since that is also changeable. Buildings breathe. So when the light hits the side of the building expands, and as it does that, so does the geometry of the detector changes. And when that happens, the signal also changes. So we have to be able to respond on the order of seconds to things that are happening on the beam line. And so we have to have some sort of data quality monitoring that's very responsive to what's happening. Further than that, we need to be able to get data quality monitoring on what kind of science we're seeing. And that we need to order minute to 10 minutes. We usually acquire data in 10-minute chunks just to make the analysis a little bit more manageable. I think they would do it continuously if they could analyze continuously, but right now it's kind of a 10-minute cadence because these are chunks that are digestible. So it's a little bit of the tail wagging the dog. During the off shifts, users will run multiple passes over the full analysis over the data to see if they can understand what happened in the last day and plan the next day. And during the 4 months after the experiment, they analyze the data and prepare publications. Usually after about 4 months, we notice that people are not touching their files as much anymore. And so they either have gotten to a publication or don't understand their data and are moving on. So that's the 4-month time scale is dictated mostly by how long it takes to get a publication out. After 4 months, we do put data on tape. We put data on tape immediately. I should say that. We put data on tape immediately, we archive it. But after 4 months, it is no longer available on tape, but it can be recovered from tape if you need it. Sorry, it's not available on disk. We can recover it from tape onto disk so that people can analyze again if they get more data and they want to analyze the data sets together. All right, so what makes this challenging? What makes this massive data analytics? So the LCLS-II upgrade, so the linear coherent light source was sending down pulses at 120 hertz. So 120 times per second, we get an X-ray pulse. Each pulse is an independent experiment, is independently important, has to be analyzed within its own context. And now we're going to a megahertz. So this is a pretty big leap in data rate. Our raw data volumes are going from what on average now is about 2 gigabytes per second to the order of 200 gigabytes per second. And very shortly after that, we expect to go to a terabyte per second coming out of the detector. We anticipate recording data volumes to be now it's 2 gigabytes per second. Very soon, about 20 to 40 gigabytes per second, and ultimately hundreds of gigabytes per second. In terms of computational requirements, most of our experiments, so you can see on the right side, we made this lovely bubble chart. So this is representing the whole of LCLS experiments, all the beam times. We've run and benchmarked all of the different types of experiments we do, the types of experiments, the classes of experiments. And we figured out how much compute power each experiment requires, given the number of passes over the data everyone makes and how complicated the analysis is. We find that most experiments, the bubbles are below a petaflop. So most experiments require a petaflop or less data, which is not computing, which is not too bad. But there's these 20% of experiments which actually require something close to the exascale at megahertz. And we have to be able to handle those experiments because those are photosynthesis 2 experiments. They are the ones that are going to figure out how to convert light into stored energy inside a plant. And these are very important for the future of the country. You have to do those experiments. That's half the reason this thing is built. And we don't have the compute on site to do it. So what do? We have a solution for that. We stream it out to NERSC or some other leadership class facility. We also use Argonne for some things, and we use Oak Ridge for some things, and we also stream data to JLab. So we surge the data offsite and we analyze the data elsewhere, where there is a significant amount of computing available. So the variability of the experiments and the data sets is important. It changes every week. So every week I have 2 or 3 experiments running, and they're all completely different from the ones that ran the previous week and different from each other. I have detectors there that are reading out between something like once per minute to a megahertz, all at the same time, and they all have to be aligned, and I have to know how many shots were acquired and which shots were acquired during that minute. The data complexity, since I'm reducing the data on the fly, the data is variable length, and it's compressed, so it's not aligned, so it's complex. And the analysis is a mix of tried and true techniques that we understand to machine learning and other innovative techniques that are less well understood and don't fit into a neat box. Coupled with that is the fact that this is a diverse community of scientists that want to do science, and they want to get to publication as fast as possible. The development cycle has to be fast and flexible, and it has to be suited to people who are not in a position to mount a significant computing effort. So this is not big high energy physics where you have built a community of people who are just sitting in front of me here who do computing and data for high energy physics. It's a beautiful thing, this. I don't have that. Most of my users just want a just do it button, and they want the data to come out the other side. They want to interact with the science information, not with the data itself, not with the detector, not with the calibration. And so we have this pressure to not leave any user behind, enable all of the science, and make things as easy to use as possible. So we've tried to strike a compromise there. We built this data system, and here data flows from left to right. See, I have no cute pictures like Maria Elena. I apologize for that. I have these block diagrams. I have these detectors on the left side. There's something like 20 of them usually that are connected up the little triangles. Data flows from left to right. About a terabyte per second comes out of that, goes through this little farm we call the data reduction pipeline. This is a CPU layer that does the online data reduction. Takes, just like Fermi did 10 kilohertz to 1 kilohertz with 3 B80 RAD70 processors. We use about 80 CPUs to reduce data and get it down by at least a factor of 10, often better than that, before it hits NVMe and it goes to storage. Coincident with that, we have online monitoring, so we have the ability to watch the data that goes through. There's a graphical user interface for this. This is very important. It means that people can click to set up an analysis, and immediately see what's going on. So if they move a motor or move a mirror somewhere on the beam line, they can immediately see something move on the screen. And this is important for basically human in the loop operations, which we currently rely on. And the problem is that we're trying to engineer out the human in the loop things. So that, because those are limiting factors. So as we go through this process of upgrading the data system, we're going to do more and more closed loop stuff, requiring more and more real-time feedback. After the fast feedback storage, which is essentially a buffer, things move offline. They can either go to our local Slack shared science data facility, or S3DF, where there's plenty of storage and some petascale computing available for us, or we can stream it out to offline storage at NERSC and use for either Perlmutter, or we can also use some other leadership class facility. And note here that every arrow represents a lot of work. For example, ESNet is that one little arrow on the bottom. And I think, Chin and Eli, who are here, will tell you how much work goes into that little arrow right there. So a word on this data reduction pipeline. So we're doing data reduction on the fly. Because we found that most of these experiments boil down to about 20 experiment types. And of those, there are probably 5 techniques that do no harm, that don't affect the science, that are palatable, that the users do when they analyze their data offline. And so we adopted those, we moved those into the online pipeline, made them performant. Those are, lossy compression, using fixed error bounds, lossless compression, trying to get to a factor of 2. Some minimal feature extraction for, in some cases, region of interest. Trigger a veto, we can veto events that don't have hits. And sometimes you can sum things up, you can add things up and do multi-event reduction. An important feature of this is that we leak unreduced data out. So you can have pre-scale data that you can look at to make sure that you haven't screwed anything up with the data reduction. And we also have the software trigger nodes that can do an event build on the fly, which you can't do a megahertz for the full event. You can do a full event build of megahertz with the amount of computing that we have available here, but you can do a very small event build with small amounts of information to decide whether or not you should toss out an event or keep an event. So we have that capability built in. So we have underneath this data management pipeline, basically, that takes care of presenting to the user a very easy interface, a web interface that lets them interact with most of the tools that we have. Underneath it, Lucio, a file manager that records whenever we start a run, stop a run, where the data is. And then the e-log that we have lets people set up analyses and workflows and trigger them whenever the data starts arriving somewhere, or the data stops, or somebody hits a button, or the coffee's done. You can basically generate any trigger. There are a number of triggers you can use to launch workflows, either locally or remote. So, like I say, we are trying to get to this mode of running with the human out of the loop. And in order to do that, we need to start moving some of the intelligence that we have in our offline and in our data reduction into the detectors themselves. And so we have people who build lovely detectors for us that can operate at very high rate. They have ASICs and FPGAs on them, and those we have access to some of the resources within those FPGAs. And so we are going to use them. The first order, we want to do some pedestal, some corrections, some calibration. The second order, we want to do some machine learning. We want to make a decision there. We want to put in some knowledgeable algorithm that can decide, is this event interesting or not, keep it or toss it. Is this an anomaly? Is this interesting? Should I vector this to a different piece of software than this other event? So we're developing these techniques to be able to be very flexible at the edge in the FPGA right next to the detector. And in this way, we can couple with the data acquisition system and actually send feedback, analyze data, can send feedback back into the DAC system and adjust how we take data and make the instrument dance in a way that we haven't been able to do before. So this is an example of just a high rate analysis going from left to right. So there's a picture of the detector. We're expecting you can get several kilohertz now out of these multi-megapixel detectors. The data reduction pipeline just rolls out the things that don't have hits in them. And then the data analysis is several hundreds of petaflops, requires a lot of Perlmutter already to analyze. So the workflow that takes the data out to NERSC It was built by the XSL project, and it turns around the analysis in minutes. It runs on several 100,000 nodes, which for us is kind of a big deal. But it's all transparent to the user, so the user doesn't see any of this. They only know that they have selected NERSC as the place where their data is going to be processed. So behind the scenes, there's a lot happening. There's data getting transferred. There's automated run processing that's launching jobs in a complex workflow, and then sending those results incrementally back to Slack to show up in web browsers. So the user only knows they've started taking data, and here in the web browser, I see that's, I see my density map is starting to fill in, and you can watch the results update during the experiment. We've also tested this by sending some data out to Jefferson Labs, so we're testing out a new path for data migration. Another thing that we realized is we're trying to introduce more AI/ML because that is the way to cope with high data rates. And we're trying to implement a lot more AI/ML at the edge, since the closer you can get to the detector, the earlier you can do your processing, the less data you have to move. And it turns out that some of our data producers, they produce hundreds of gigabytes per second of data, but realistically, each event is like eight numbers, 8 floats. So you want to take these hundreds of gigabytes per second, these huge waveforms that come out, and get it down to 8 numbers, which represent the salient information about what happened in that event. And so we've developed a neural net that goes into an FPGA that sits at the edge and it spits out this data. And the problem that we learned is that over the course of an hour, the building will breathe, something will change about the sample, and all of a sudden you have to adjust. And so what we're doing is we're sending our unreduced data out to Argonne, to a specialized facility there, where it can retrain the model very, very quickly within minutes, and then send those new weights back so they can be implemented at the beamline within minutes. So this is an example of how trying to take AI/ML and use it in this rapidly changing environment introduced a whole new workflow, a data-intensive workflow with some very real-time constraints that we had to learn how to cope with. So we have a system for dealing with it now. It's great. It's working quite well. And so we'd like to expand this now into other experiments. So I know that Ginny talked about this, and Ginny talked about this a little bit, but I wanted to put in my own plug. So like I say, we can only do about 80% of our experiments locally. So the S3DF is a resource for our users to do data analysis. But at the end of the day, we have 20% of our experiments are going to go elsewhere. And NERSC isn't always up. Sometimes it goes down. So we have to have that resiliency. We have to be able to fail over to other OSCAR facilities. Luckily, OSCAR has stepped up. They have gone through this exercise of trying to collect everyone's requirements and come up with an integrated concept for an integrated research ecosystem. And part of which is the central part of which is this high performance data facility, which the call just came out. And right now, what we're looking at is, we want to make sure that we can participate in that ecosystem and use those resources for our bursty, nasty jobs, because they spin up 10 minutes and then they crash down. 2 minutes later, they start up again, come down. 10 minutes, they come back up again, and then we're down for 3 hours. We are not good users of a common high performance data facility. So we are very bursty and inconsistent in our usage pattern. Nevertheless, we want to participate in this ecosystem, and we want to make sure that whatever it is that users interact with at NERSC, they have the same tools available in the S3DF. So we want to make sure it looks the same. So if there's one thing that I want you to take away from this, it is that we're doing cool things on the light sources side. We're just making that leap from like single scientist with a USB stick and a laptop to an absolute mountain of data. So imagine that just a few years ago, you literally would just sneaker net all of your data home. You detach your hard disk to your computer, and that sits at the beamline, and you copy the data, and then you just walk off with it, and you analyze it on your laptop. And here I am today, and I'm saying, no, you got to use a supercomputer. You're going to use an exascale computer to do your analysis. That's a huge leap for a community to take. So all of the tools that we're building are trying to make it as easy as possible to use, as consistent. And I think the HPDF is going to be a huge part of that, because it's going to make this entire environment of local and remote resources look the same. And it understands the real-time constraints that we have, and will give us seamless access to lots of things. So I think a lot of the problems that I heard about from the SNOMAS report, resonated with me as well for this community, in that we have a workforce problem. We don't have enough people who can program things that's for the edge and for HPC. And we have to make things as easy to use as possible. And we want this common software ecosystem, but it is difficult to achieve, especially for us, where at some level, every user is a snowflake, every user is special. They all have some experiment specific thing. And so we have to do the common stuff common and then the special stuff easy. So that's where we're at.
Thank you, Jana. Questions? Yeah, we talk about herding cats in HEP. You face the same.
So a couple slides ago, you mentioned shipping data to Argonne, was it, to retrain the AI model? My question is, do you do that kind of continually? If you do it periodically, do you have like some criteria when you recognize there's enough difference to retrain?
So, yeah, the intent is to do it continuously. But it is currently it is bunched, it's a file. And so we write a file that's the prescale data, reduced data, unreduced data. And then we ship that off and we analyze it, we bring it back. Ultimately, we're going to stream that data. So as soon as the data starts, we'll start the model training and we'll just keep a steady flow of data going until the data stops. It is still segmented because the way that users take data, they sort of do it in these 10-minute chunks because it makes the data easier to analyze. So there is still this sort of artificial chunking that happens just based on how users use the beamline. But yeah, I think ultimately we really want it to be streaming, where it's just going and coming right back.
Hi, thanks for the really nice talk. I'm actually really impressed because I think this is so cool that like there's these really high data rates and you're like handling it by like all these like, you know, different computing innovations. My question was that because like you have such a wide variety of like different experiments that are being done, like different like scientific needs, whether like you adapt like the lossy compression to like suit like whatever experiments, you know, requesting data from your facility.
Yeah, so that is worked out with the experiment ahead of time.
Okay.
So we have looked at all of the experiments that come through LCLS and basically decided, you know, which ones are, which types of data compression are most suitable to which type of data. And then we talk to the user group and we say, if we use this data reduction, what does it do to your data? Because they usually have canned data sets that they can say has an effect, it doesn't have an effect. A lot of like the SZ compression, the lossy compression you can dial in error bounds on your data. So if you can tolerate a little more lossing, a little more error, then you can get quite a lot of compression. And so we try not to punish users we do what's right for the science. Our only constraint is that we have to fit in the pipe. We have a few hundred gigabytes per second, so we have to fit in that pipe, and we have to be able to write to disk, just the real limitation, because it's harder. It takes money to scale yourself out of the network and storage problems. But yeah, it's something that's decided ahead of time with the user, and then they dial in parameters during the experiment and suit them for that experiment.
Yeah, thanks so much.
You said that when nurse goes down, you actually fail over to another.
Ideally, we do not currently fail over.
You don't fail over.
Currently, we fail. Just no. Right now, we can always do data analysis at lower level at SLAC. So we do have a local compute facility. It just can't keep up with the full megahertz for some experiments. So currently, if nurse goes down, we'll revert back to SLAC and we'll just do a subset of the data. But in the IRI picture and this integrated research picture where all of the OSCAR resources are there and available to us, in a perfect world, I would fail over. In a perfect world, if nurse isn't there, I'd go to Polaris. You know, I'd go over to Oak Ridge. I'd go to, you know, I would use somebody else's resource.
But as you said, the requirements then on uniformity are really large across
Yeah.
the.
Yeah, this is not an easy problem.
I was wondering, what is the total cost of ownership of your local facilities? Like, how much did it cost to put down your data pipeline, the local part?
So there's the question of cost of the the data reduction pipeline.
Well, everything that you have on site at SLUC.
So the cost of the data system for the beginning of LCLS-II was of order 17 million. That is not enough for a feature. So it has to expand. It's going to be another, 10 or 15 million ultimately to get it to LCLS-II, which is the next upgrade. Where it goes beyond that, I don't know. Our funding is very much project-based. And so the project is what pays for the computing. We don't have a very nice model for continuing engineering. The goal is to replace our nodes every 5 years. That's a goal, and it's not necessarily matched by the funding that we get from BES. And so that's a constant negotiation. That's a yearly negotiation. And a lot of it just comes from various projects that we have. We find a few $100K here, a few $100K there, cobble it together. But we're hoping that the core of the system can be built on that few tens of million.
Thanks.
One more question.
Hi. So my name is Patrick. I'm from DAISY. We are running the Petra 3 facility and the European XFAL. And I was thinking in your slide on data lifecycle, yeah, you mentioned that after 4 months you're storing the data on tape.
Yes.
But this is only the first part. This is only a prerequisite to make it reusable. So are you forcing your Beamline scientists to provide data management plans or to provide a reasonable amount of metadata, give DOIs to the data, and all the fair data thing?
Yeah, the fair data principles. So we don't, our data, I should say, we're in a different situation than Europe. So in Europe, everything has to be public after some embargo period, right? We don't have to do that. For us, the DOE keeps telling us the data belongs to the user. Except when the user tries to take it off-site with their USB stick, we kind of laugh because it won't fit. And so, we have a data management system. We have the ability for users to put in metadata and to write it down, but it's for the users only. So it's not a generic lead. If I were a different experimenter coming in and looking at somebody else's data, I would have absolutely no idea under which conditions it was taken or how to analyze it, which is unfortunate.
Okay, but there is a difference between fair data and open data. So you can have fair data and it does not necessarily be open. Nevertheless, being fair is very, very helpful, even for industry and for, okay, thanks.
So in answer, so we do have some metadata collection that's standard for every experiment. So what number of times it was taken, sample name, what the experiment was, various other things that are collected automatically at the time that we acquire the data. If we process the data and do anything to it, we store that as well. So any data reduction or any other processing that happens on top of that, that also gets stored as part of the chain. Beyond that, we provide the ability for users to capture that information and publicize it, but we do not require it. It is not a requirement from our funding agency. Yes.
Okay, let's thank Jana again. Okay, now Rosie Bolton. Bring up. Just remind you again, stick around after Rosie's talk for the poster awards.
Mouse click, you remember? So I passed the first test.
So global data management in astronomy and the link to HEP. Are we collaborators, consumers, or competitors? Take it away, Rosie.
Thanks very much. So thank you very much for having me. I was reminded to introduce myself properly before we carry on. So my name is Rosie Bolton. I have a very grand title as the head of data operations at SKAO. SKAO does not take any data yet, so it's actually quite it's quite a simple job. But I'm the chief person with the worry list around particularly our offsite data management plan. So I was asked to come here and talk about data management in astronomy. So rather than just talking SKA, I thought I would be ambitious and extend that to include also Rubin Observatory, LSST, and also CTAO. So I come here wearing one hat and trying to represent 3 different projects. I would do it badly. There will be things I get wrong, but you know, bear with me. Could we have everyone in the audience who is representing or working on SKA, CTA, and Rubin LSST, just like wave your hand around, because there are a few of us. And the alternative title would be, I'm an astronomer, get me out of here. So to all of those of you who are involved in these projects and identify as being an astronomer, well done on making it to Thursday of this week. I'm going to try and continue the justification of why we're here. There's been a load of great talks on these projects already within the individual tracks. I'm going to try and bring them together at a very high level picture. So just to set the scene for the 3 projects I'm going to talk about, CTAO will be a ground-based gamma ray observatory, which will start operation around 2028, number to be confirmed, with a 30-year lifetime. It is an experiment to detect the cascades of torrential radiation that come when a gamma ray interacts with the atmosphere. I am not an expert in this, but I think it's really exciting. So it's a really nice instrument. There will be 2 arrays of telescopes to catch these showers. One will be in Chile in the southern hemisphere, and one will be in La Palma in the northern hemisphere, and that gives sky coverage around the world for these showers. So very exciting project. It will act as an observatory, and it will be proposal driven. So science teams will be submitting their proposals for ideas, and as a result, the antennas get pointed in particular directions to try and catch the cascade that they're interested in. So more information, jump onto their website, and I will have stolen stuff from CTAO's website as I go along. I should also shout out the CTAO collaborators that I've been in touch with, Gareth Hughes and Matthias Rusling. Thanks to them for some slide material that is in here. As opposed to CTAO, LSST, or Rubin Observatory, as it is now known, and with possibly the best rebranding ever, LSST actually now stands for the Legacy Survey of Space and Time. It was the largest synoptic survey telescope, but they saw an opportunity. And actually what it means is that the first focus of activity for Rubin that will happen over the 10 years from 2025 is to conduct a legacy survey of space and time. And that means visiting and revisiting the sky to take images of the stars again and again and again, and process those to see what changed about the sky and what do you get if you keep adding those images together to go deeper and deeper. And then really significantly extract the information from those time series images and from those stacked images to work out what that means for astronomy in terms of catalogues. And it's those products which are then given to the science communities for them to then do their work. So it's not a proposal-led system, it's a system that is a 10-year survey which will produce a legacy data set to be used and reused again and again by science collaborations. And I'll talk more about what that means in the next few slides. The way that the LSST is developing the survey is through interacting with collaboration teams that are already existing. It's a back and forth iterative approach to develop a survey strategy that meets the scientific needs of as broad a community as possible. So there are 8 different science collaborations, and they all have different things they're interested in. Some might want to see, did the brightness of the galaxy change, from 1 hour to the next, and others might want to look at long-term variations in brightness of stars or galaxies. And they are in an interactive model discussing a survey strategy. But once it gets started, then it's really important that the data sets coming out are consistent. So you know that you've got particular cadences of visits to parts of the sky that are going to give you a consistent data set that will produce the legacy aspect. And I think that's really important and exciting. SKA. So SKA is going to be the world's largest radio observatory for now. The US is probably going to take over at some point, but we live with that. It's under construction now, really exciting. We've had the first couple of hundred of antennas in the low frequency band deployed in Australia in the last couple of weeks, so it's really exciting. So we're starting to build it, which means we've got the funding in place to make a beginning as well, which is a significant step. It's been under discussion for decades, so now we really are putting things on the ground. The two images with multiple antennas are artist's impression. This little image on the left of the slide there is a real picture. The SKA is two array telescopes with 2 interferometers. One of them will be consisting of 200 or so 15-meter diameter dishes spread about 100 kilometers across the South African desert. Those will operate in the gigahertz frequency range. And then in Western Australia, there'll be a complementary array of 130,000 low frequency antennas that are spread over about 60 kilometers. And those again are in a desert site where it's dry, but more importantly for a radio where there are very few people, so no mobile phones, no radio noise, as little as possible. And so those don't work together particularly, but between the two arrays, they cover a broad range of frequency space and, very importantly, redshift space. So with this low frequency antenna array, we can go right back to the epoch of reionization to see when the very first galaxies started, the stars started burning the hydrogen, and we will hopefully observe that in the process of happening by looking at low frequency when the hydrogen redshifted all the way down to 100 megahertz. So it's a pretty exciting project. I would say that I work for SKA. I have to say that. It supports a very broad range of science use cases, and it is an observatory. So again, similar to CTAO, it is open for scientists to propose what they want to look at. And those proposals could range from someone who just needs a couple of hours of time to large consortia that might need several thousand. We've got ambitions for 10,000 hours of survey time to look at huge portions of the sky to seek particular signals. So it's a broad mix of science that we've done, and there'll be an annual call for proposals, but those big projects are likely to be multi-year projects going on. So super exciting. I don't have time for the science. What I wanted to focus on today was the similarities and the differences between these different projects, because I think it might put into context why we come to SHEP and why we're interested in some of the tools that you folks in high energy and nuclear physics are looking at. So I've thought about this in many different ways, and the view that I found really helpful was this view I found on the CTA website, which shows kind of science operations flow. So I talked before about how the users, which are on the right-hand side here, write proposals, they go in to the observatory to be assessed, turned into planned observations, and then those observations are carried out by the CTAO itself. They're not done by the users. There's a break there to make sure you don't waste time doing junk. So then those observations are taken dynamically, and then pass through a series of data reduction stages, in the end making sure that if events happen and a trigger goes off, that the correct data products are made available to the science users from the science archive down the bottom. So that's very briefly what happened for CTAO. Because CTAO was waiting for triggers to happen, the actual, you get a data reduction process, which is throwing away the junk as you go along. And in the end, the data product rate coming out for the users is relatively small. So you might start off with 1,000 petabytes a year being taken at the dishes. By the time you've gone through these stages of throwing away the stuff that you don't think is interesting, you're down at 10 to 100 terabytes per year in the science archive. And that's important. Another interesting thing is that CTA will be able to send trigger events out to other observatories to say, hey, something just happened over there. Everyone go look, see if there's something that you want to look at too. And the other observatories, such as SPA, are listening to those triggers to say, yeah, sure, we'll override our operation and go and look just to see if that bit of sky is interesting in the radio or in whatever way you found it. So that's in a nutshell. And so because I like this diagram so much, I've spent a lot of time on my journey over here trying to recreate them for LSST and CTAO. So bear with me, it's not the same shapes involved, but it's a similar thing showing the flow, right? So as you go from left to right in this diagram, as with the previous one, we're talking about complete site control, which might be at the high side, in the remote side, observatory operations and data facilities, which might be external data centers, but again, under observatory control or, you know, contract, if you like. And then less controlled scenarios as you move further out, eventually to the outside world, here be dragons, you know, science users live here. So I'm trying to show how it works for LSST here. So again, science users are involved, top right-hand side, building those science collaborations. Those are affecting the design of the surveys. And so there's a dotted arrow there into survey planning and science operations. But you know, by the time it gets to there, then it's like, right, fine, leave it with us, we'll get back to you with your data when we're done. Data are taken at the observatory site in Chile. You know, the Rubin Observatory is responsible for that execution of the data, and then needs to do data processing of raw data. So I nearly said data reduction, but I know from Fabio's talk, it's not reduced for LSST. In fact, the data volume goes up every time the processing touches it. So the raw data goes up by a factor of 3 when it gets processed, which I find quite interesting. But final observatory product generation happens within data facilities, and there's a handful of those around the world. And then once those data products have been made to the satisfaction of the LSST, so those would be the time series events, the co-added data to see the full depth of on the sky, and the catalogs, then those can be made available to the users in data access centers. So data access centers can be part of LSST collaboration, or they could be independent, and the independent ones are called IDACs. Those are essentially science archive access points for the users, and those are users with rights to the data. So the data is proprietary for, I think, a couple of years before it becomes public. But eventually public users could also access data products via those data access centers as well. And again, we have a dotted line, science alerts can go out to other observatories if something goes bang out there. So there's a standard protocol for doing that. It's provided by the IVOA, which observatories are all listening out for. So that's the LSST story. Obviously, I work for SKA, so I can do a much more complicated diagram for SKA. However, too long didn't read. You don't need to see what happens inside, but it's there on the PDF if you want it, so I left it in. Again, for SKA, we have science users sending their proposals in to the observatory that will then undergo proposal handling, like deciding who gets to have the time. And then the big box here is observatory data taking and data reduction. Genuinely, it gets 40 times less in our data processor to output data products to the best of the ability of the observatory. They should be exactly the science-ready products so that to go into the archive. It's not quite true, but we can talk about that later. Things to note for the big box of stuff are that it's a quarter exaflop machine that, well, in total, there's 2 sites running that supercomputer. It's a quarter exaflop, roughly, and there's also a 50 petaflop streaming correlator, basically, to do real-time data analysis before we do the science product generation. So it's a complex picture. We expect to output between 200 and 600 petabytes a year of science data products from the observatory, and we output them into a network of regional centers, so SKA regional centers. So as we move along this diagram from left to right, the regional centers are not the outside world, but unfortunately, they're not within the funding of the project. So they are a collaboration that we're building to deliver science archive capabilities to our users, and we are collaborating as an observatory to try and, to support how that's done, which looks a lot, at a high level, it looks a lot like WRCD. We want a pledging model of resources coming in. We want to understand how we share the burden of doing user support and science analysis in these regional centers. and how we sort of keep it balanced. But those centres are essential for the running of the observatory because we don't have any other way for users to get to their data products. It's feasible, although unlikely, to write a very good proposal, but it is feasible that a single SKA image cube, so an area of the sky with a bunch of different radio frequencies, so SKA can do 65,000 frequency channels, and it can do images 50,000 pixels on the side. That's a petabyte of data if you include all of the different axes. That's a lot. So yeah, there's no USB sticks going on here. There's no magnetic tapes you can just ask to be posted. We need to shift a paradigm where the user access is all via SKA regional centres. And similar to the previous talk, we need to provide tools for those users to sort of have some uniformity of access, that they have a reasonable experience doing that. Again, SKA data is proprietary to the teams that wrote the proposal for the first year or so, timescale to be determined. Thereafter, it becomes public. So one of the key functions of the regional centres really is, again, legacy. You know, it's a 50-year lifetime project. Well, for 49 of the years, the data, you know, the first data is going to be public more. So we expect most of the science in the end will be done on the public data. Sure, you'll get the data that you asked for. You know, you wrote your proposal. Many of us would have written proposals to do stuff, and it turned out the thing we learned wasn't quite the thing we thought we would learn when we were planning it. This is the case, we think, for SKA, we need to be able to support innovative reuse of the data products. So the FAIR principles are really important for us as well. I'm talking too much about SKA. The point is, again, we have the science alert thing as well to other observatories, and I should have made it a two-way arrow. We will listen for the science alerts. So I promise you will listen to other people. Okay, I think it's worth considering the physical view of this as well, because it talks to the challenge of the data management. So for CTAO, the physical view is that you have a site that's in Chile and a site that is it's in Spain, but it's actually the Canary Islands. So it's an island site of Africa, which you can't see on this map. It is coloured red. And then there will be movement of data into the data facilities, which will be in Europe. And it's at that site that the observatory is under control of the processing. So doing its observatory processing to reduce down the data to only the significant activities, I guess, the data that the users want to get out. And then the users will be able to receive that data when they're done. So almost all of the observatory computing is undertaken by CTAO staff, because by the time it gets to where the user needs it, they actually could probably put it on a decent USB stick or a hard drive. It's actually doable on a laptop or a small university cluster by that point. So CTAO doesn't quite have the headache of how to support users analyzing the data products that they're giving them. But they will keep the products in their data centers too, so that enables some reuse. The physical view for Ruben LSST is that the data capture happens in Chile, data production happens in Tucson, and then there are data facilities at SLAC, at IM du Pétois in France, in Lyon, and at IRIS in Edinburgh in the UK. And those data facilities have a shared responsibility for data product generation in a 35, 40, 25 ratio. And those are agreements that are firmly in place. They are part of the observatory processing. And the observatory is responsible for the data product generation and the quality of the software. If they screw up, it's on them. Like the users are, the end users are not responsible for that. So they have to get them done. So this is work in progress, as you have heard for the multiple talks on LSST during this conference. However, there's the next physical view, which I think is important, which is easy to overlook. So this is in the observatory. If you now just look at the map and then see the green sites here. So the green countries are countries that at the current time, as far as I know, are anticipating hosting one of these data access centers. So those are where the scientists can be accessing data products from LSST. And there's not a requirement on those data access centers to be performing observatory functions. So it's not the same level of agreement. They might hold a copy of the data, but they wouldn't be being relied on to hold a copy of the data, which is an important distinction. The physical B for SKA is that we will have sites in South Africa and Australia, so the red colours here, but we have involvement from countries spanning the globe, so 16 or so at the moment. And we want to build a network of regional centres that support the users doing this. So our principles for doing that are that we will have, we hope, a commensurate share of SRC resources that matches the SKA contribution. So if you're a 10% stakeholder in SKA, we hope you will put in 10% of the global resources needed to do SKA regional centres, to do science archive work. Want to have a federated, interoperable set of resources that together give very high availability, integrated with the help desk of SKA and supporting open science principles. And importantly for data management, a centrally run replica management and data lifecycle. So collective responsibility to say, no, we will between us make sure there are 2 copies of every data product somewhere in this ecosystem, which is different from the data access center model for LSST, for example. It's closer to the data facility model, but we don't own these sites or have any financial transaction with them. So it's interesting. It's an interesting challenge. The idea is to send users to the data wherever possible and avoid any unnecessary duplication. So I'll just briefly touch on this because it's a bit of a vanity slide. In the receivers for SKA, which is in pink here, you actually have something like 8 zettabytes annually of data. But of course, it gets thrown away vastly. But it's just fun to ever get to a number that has zetta. But the headlines to take home are we're talking about 100 terabytes a year coming out of CTAO, 50 petabytes a year or so from LSST, and we think 600 petabytes for SKA. And then we have to also add on user-generated data products as well, which for SKA could be another couple of 100 petabytes, we think. So PEP, why are we here? Data management is the most obvious thing from my perspective for PEP. So for LSST, they will use Ruscio to do the replica management between those facilities that were within the observatory. And there have been some nice talks this week about, they've touched on the concept of the data butler, which is the service to translate the local copies of data into a local database and then allows the batch processing to run locally and then upload the results, but not the intermediate files, back into the Ruscio database. So you get replication of the results between those data facilities. So Ruscio, clearly a tool of interest here, and it could also be the mechanism for delivering the data into the data access center as well. Okay, 2 minutes. For CTA, again, lifecycle management and planning for location of data products is a key thing. So they have a vision for where they want data to go from one line to the next. They want to share the load between their data centers. They need a way of writing rules for it that that reflect the life cycle and the locations of those sites, and allow sort of forward planning of placement. And Ruscio again is a good example of a rule-based system that speaks the kind of language that operators of these projects want to speak. I can understand the way that the Ruscio rules are written, so it's very good as a way of bulk data distribution for that. And for SKA as well, we foresee scenarios where we want to plan ahead for particular projects, which SRC locations should take the data from one group's proposal. So project 316, yes, we want to make sure it all goes to Canada. So you can plan ahead with the metadata placement in Ruscio, put it all in Canada, and allow data placement that way. So that's a nice example. We could then plan our processing for those projects at a particular site, and we want to use that ability to plan which users go where. Could be based on the hardware of the local site, could be based on just who's got space to store it right now, or it could be that that's the SRC that's the closest to where the user group is. It shouldn't need to be. Users should be able to be sent exactly where the data are, but there might be reasons why, just because it feels nice, you want to make sure that your local team has their data on your local site. So it could be done like that. But we also need to make sure that we can cope with global execution, so moving compute to the data, so a single workflow, running primarily at one site, but launching multiple sub-jobs and then bringing the results back. We don't want to translate these data products from one site to another unless we have to. They're much better to be able to accept jobs in a subgraph and then send back the results. And we also need to consider how we develop a content delivery network, essentially, to allow users to interact with the data products, to play with them, to visualize them. So even though the products that they want to visualize could be in multiple different places, we have to figure out ways to do that. Very briefly then, data management legacy of the Escape project. So we kind of cut our teeth in Escape for the last few years. You know, we learned how to play in the hex sound pit, if you like. It helped us learn the fun we could have with Ruscio, for example, by giving us access to the Escape data lake. And it led to some community data replication and data access challenges within Escape, which were really valuable. I speak for SKA here, but I think it was a shared experience for CTO and LSST colleagues. That was really, really good. As a result, SKA now has its own Ruscio prototype running. So this is the graphic of the sites, countries involved in SKA, and I'm now going to overlay where we have people running storage in our Ruscio sites, and it's pretty complete. So we've got a lot of countries that now have very small Ruscio storage elements, you know, involved, but they are happy to be part of the system playing. And there are real people involved here. So I put the picture of the faces because I think that people are really important, and we're building a software development community, you know, moving towards getting ready for the SKA to come online in 2028. So this is the coverage of our Ruscio testbed now, and it's helping us build towards data challenges, essentially. We've seen a few data challenges mentioned this week. It's something that SKA needs to get on board with sooner, as soon as possible, but we have some tools in place to enable that now. So, last slide, intended take-home messages. Global data management is a shared concern, obviously, and CERN and WRCG and others have paved the way. But there are several upcoming astronomy observatories that will face similar challenges to you. So are we collaborators? Yes, and I think we are, we really are. The Escape project has been brilliant. It's been like the nursery slope that's useful to get on board with that. In spite of lockdowns in Escape, we built a really genuine collaboration, and those personal connections that we made are so valuable and are going to help us in future developments. Are we consumers? Can you just say, well, we've done it, just copy that? We are, but I think we have to be mindful that it's not quite a one-size-fits-all situation. There are differences in data set size, in file size, in governance and control, and in the user access patterns that we might be considering. Are we competitors? I hope not. We will not be competing for the same links, for example. We won't be jumping on board all your bandwidth. I can't imagine a way of direct competition, but we will put pressure on shared sites. So we have to be careful that we're not saying you have to build, we need 16 racks in this data center, and there's already not space in the building. And it may put pressure on development of tools. So, if we're looking at Ruscio and FTS and DIRAC and Panda and a variety of other things, we can't just assume that HEP will suddenly make them work for the use cases that we want. And I think we have to show that we're prepared to collaborate and put FT developer effort into building those tools together. And I think that's it. So thank you very much.
Thank you, Rosie. Questions? Hello.
Paolo Calafiura, Berkeley. So maybe we'll be competitors for experts and people to work on all these problems. But no, my serious question was another one. So 600 petabytes plus 200, 800 petabytes per year. Are you going to publicly release 800 petabytes of data every year? And who is paying for the networking and all? Or are you going to do like the LHC experiments, which only release the very refined, the final products of data?
No, that is. So devil's in the detail. We can talk later, but it's drinks tonight, so I'm not saying I'll keep talking for too long. So the 600 petabytes a year is more or less what you get if you fill a 100 gig link from each site, more or less, plus or minus. Right? 200 petabytes a year is the minimum number I estimated by looking at the data product outputs of a whole mixture of different science cases. So that would be a probable minimum. But those data products all will be sent to the network of regional centers. So if I go back to this plot here, those all end up in those regional centers. At which point, when they're public, then anyone should be able to find them and maybe visualize them, but they may not be able to run large processing because they may have to request an SRC project then to get a bunch of computers to do that.
Oh, so they will be public, but they will still have to apply to be able to run on the SRC or something like that.
They'll have to apply if it's a significant amount. What we'd like to do is leave the door open a little bit so that you start off saying, well, if it's small, that's okay, and then over time, what we call small will hopefully grow. But if someone wants to do a machine learning reclassification of every single image that was ever done, that's probably going to be huge. We would expect them to be putting in a proposal to the SRCs, to the network of SRCs, to say, I've got this idea, it's going to deliver loads of science, but it needs to be pledged in some way. Okay.
About those regional centers, do you see them emerging and scaling up on a timescale compatible with the succession of bigger data challenges you'll have to do between now and 2028?
Hardware-wise, do you mean?
Pretty much hardware-wise, money-wise, if you want to put it that way.
So the funding for the SRC projects is patchy at the moment, but it's starting to come in for some of them. There's a steering committee and we meet a lot. And we've got pretty good buy-in of this idea that it should be a proportional, buy-in, so that your pledge will be, proportional to your SKA share. That seems to be quite well understood, and of course, those steering committee members are talking a lot with their funding agencies to try and say, oh, if you're going to make the best of your SKA investment, you actually need a bit extra to make sure that your users can access the data. Otherwise, how on earth else were they going to do it? Like, did they really think it through? Like, you can't have a science team that is writing a proposal for 100 petabytes of output data product without a plan for the data management. So by forcing this SRC ecosystem, I think it's an opportunity actually to make sure that we get homogeneity, not of resources, but of software and provenance and findable data, which otherwise could be lost in the system if it's all. As was mentioned in the previous talk, if the metadata is per experiment, you lose that ability to reuse in the future.
Hi, Rosie. Thanks for the presentation. So I have a question. You mentioned that you are hoping that when making the data open, a lot of science will be done on the open data. What are you doing in order to teach the public or scientists, interested scientists, to understand the data, to understand the metadata and get access to it? Because it's not happening out of the blue, I assume.
Yeah, okay, so that's a really good question, and I'm lucky that there is actually quite a good answer to it. So the SKA Observatory is running a series of science data challenges, which are not about pushing big data sets around, although actually they are almost now. They are about community engagement with SKA-like data products. So the first one was radio continuum images with representative resolution. So that's based on simulated SKA data, of course. And the second one was moving that towards spectral line images. So getting the science teams to interact with those. In fact, there's a third one now which is looking towards the epoch of reionization experiments, and that has been visibility based, so pre-image stage, so it needs Fourier transforming before you get an image. And that's building capability within the science teams to understand what it's like to not be able to just play on their laptop, but also real experience with some sites, what it's like to deal with SKA users or SKA potential users. And so they're not formally required to be proto-SRCs yet, but we hope that some of the sites will be the same site. So the Swiss sites, for example, are likely to be the same site, and same in the UK. We have multiple sites involved that are already along the way. Are we going to get there in time? Who knows? But I appreciate you only asking for SKA, because anyone asking a CTAO or LSS-II question would be really hard.
Don't see any more questions. Yeah, okay.
This is Simone from CERN. In your last slide, I think you mentioned, believe competition, and I believe I agree with you that in general we might not expect competition, but there are probably a few if statements like competition at the level of network, at the level of facilities, etc. And in my opinion, it would be wise at least to test that this non-expected competition is actually not there. So WCG has plans for a series of data challenges in the next few years. And I was wondering if you think it's useful for you and also feasible, of course, to have some of those exercises done at the same time between the WCG experiments and SKA and CTA, etc.
I'm interested you because I know that it's data. Yes, exactly. We are not going to be ready for March 24, I don't think, which is the next big LHC data challenge, I think. I don't speak HEP, but I think that's right. But I can see that there would be value in making sure that indeed we don't knock each other out, you know, by planning on things at the same time. We have to make sure that our services are, proto services are kind of representative of what they might be in the future. So we don't, at the moment, our reshow instance is running on the CERN pilot FTS service, and Rahini's nodding. But if that's not ready for a data challenge, we could easily give us the chance that we'll try and break it. So, but we're now deploying our own FTS service. We may be able to move on to that by then. We want to be able to play with all the black boxes in the data management stack of WLCG and see what it takes to break them. So, yeah.
Okay, let's thank Rosie and all of our speakers for their excellent talk. And you stick around now for one more thing.
Thank you. So we will do a quick presentation of the student poster competition. Okay, so first, thanks to all the posters, and thank you to my fellow organizing committee who helped make sure that the posters were a prominent player in our coffee breaks, which I thought was really great. So quickly, the rules were enforced by honor. There were 116 votes cast, and based on having seen the distribution, I can tell no one cheated, so that was good. But there were clear standout posters, which also made it easy to pick the top three. And thank you to the JSA, which is the Jefferson Labs management contractor, for sponsoring this competition. So we will award the top three. I will call out the top three, and instead of doing like name, entry, applause, I want to get us to dinner quickly. I'm going to go through the names. As I call, the students can come up, and then we can do a quick round of applause at the end, okay? So in third place was Viola Cavallini. If she's here, she come right up with fast and optimized data acquisition and control software for the TimePix 4 ASIC. And in second place, we have Homa Yunia de Sosa Pereira with the Alice Glance membership system. And in first place, Leia Ruta with graph neural network-based track finding in the central drift chamber at Bell 2. Please come on up. You can clap now. Yes, go for it.
Nice job.
Okay. That's it. Thank you guys. Nice job.
And you stick around now for one more thing.
Thank you. So we will do a quick presentation of the student poster competition. Okay, so first, thanks to all the posters, and thank you to my fellow organizing committee who helped make sure that the posters were a prominent player in our coffee breaks, which I thought was really great. So quickly, the rules were enforced by honor. There were 116 votes cast, and based on having seen the distribution, I can tell no one cheated, so that was good. But there were clear standout posters, which also made it easy to pick the top three. And thank you to the JSA, which is the Jefferson Labs management contractor, for sponsoring this competition. So we will award the top three. I will call out the top three, and instead of doing like name, entry, applause, I want to get us to dinner quickly. I'm going to go through the names. As I call, the students can come up, and then we can do a quick round of applause at the end, okay? So in third place was Viola Cavallini. If she's here, she come right up with fast and optimized data acquisition and control software for the TimePix 4 ASIC. And in second place, we have Homa Yunia de Sosa Pereira with the Alice Glance membership system. And in first place, Leia Ruta with graph neural network-based track finding in the central drift chamber at Bell 2. Please come on up. You can clap now. Yes, go for it.
Nice job.
Okay. That's it. Thank you guys. Nice job.